Well, today I'm going to write you Fourier series as the sum of complex exponentials, not as the sines and cosines, but complex exponentials. And my periodic function f of x is then going to look like, it will have e to the I and x complex exponentials, many of them in the sum for the different values of n. So I do a summation over n, and the values for n will now go from minus infinity to infinity. And these complex exponentials can have and will have different coefficients cn's. So I must allow for that, just like we had an's and bn's for sines and cosines. Now we have cn's for complex exponentials. And how do we get this form? Well, we use Euler's formula, and we take that and we put that back into the sine and cosine form of the Fourier series, and after 4 or 5 lines we get this. And these cn's complex amplitudes, let me write ck's, are given by 1 over 2 pi, the integral from minus pi to pi, over which this function is periodic, f of x times e to the minus ikx dx. And how do we get that? Well, we multiply both sides with the e to the minus ikx, and we integrate it from minus pi to pi. And the idea of orthogonality comes into the picture now. Just like we had orthogonality for sine and cosine functions, now we have that for exponentials, complex exponentials. What it does it, you have here infinite number of integrals, and orthogonality says only one is going to survive, and it gives you ck's, just like that. And of course I'm going to show you that how to do it. And so let's do it. And I will start with the sine and cosine form. The function is the summation over cosines, an's times cosine of nx, and the sum goes from 0 to infinity, plus the summation over sines, bn's times sine of nx, and this goes from 1 to infinity. And now Euler is going to help us. Euler's formula, they are e to the I nx cosine of nx plus I, where I is under root of minus 1, times sine of nx, and we have another one with the minus sign, e to the minus I nx. It's going to be exactly the same, but now we have here negative sign, I times sine of nx. And these complex exponentials have their interpretations. They are rotating vectors in the complex plane, and I want to show you that how. This is your real axis, that's going to be imaginary. Then e to the I nx represents a point in the complex plane or a vector. For now, let me change x to t, time. It's easier for me to work with times, that's why I'm doing it. So let me call this vector e to the I n t, and now you might want to call n as omega, angular frequency, but you will still see me calling that just frequency. And so as the time passes by, this vector is going to go around in the circle with the frequency positive n, positive frequency in this direction. It's going to rotate like this. And you might want to decompose this vector. This is going to be sine of nt, look here, and this is going to be cosine of nt, yes, nt. What about this one? Well, this could represent a point here, or the vector at some moment in time, e to the minus I n t, and this is going to rotate with the negative frequency, negative n. Negative means it's going to rotate like this. That's the meaning of having the negative frequency in the complex plane. But you must know there's nothing really negative about that. It's just that this vector is going to rotate in the opposite direction. We need cosines and sines in terms of complex exponentials, and if you look carefully, if I add them, these two equations, you lose these two, you get twice of cosines, so you get cosine of nx, you have to add them, you get e to the I nx plus e to the minus I nx, and the two that I was going to have here will come downstairs. If you want sine, well, you can subtract these two equations, then these two go away, these cosines, and you get twice of I times sine, and so you are going to get sine of nx, and the 2i that you're going to have will go downstairs. And now you have to subtract that, you get e to the I nx minus e to the minus I nx. And since we are just adding and subtracting, these are vectors, it's like a vector addition in the complex plane. So you could have done, you could take this vector, the tail of that, and you put on the head of that if you want to add that. So it comes here, so it will be somewhere here, and since this distance is cosine and this will be cosine too, so this is twice of cosines. So that's what you get. And if you want to subtract these two vectors, well, you can flip it over by 180 degrees, then it will go like this somewhere here, and then this height will be twice of I times sine of nt in this case. I do not like this I downstairs, so I multiply with I upstairs and downstairs. So I multiply by I, it comes here, comes there, and this becomes I squared. And I squared is minus 1, right? So that minus sign comes here and this becomes plus. So now I can remove it. That's what I want it to have. I want I to be upstairs. Now we are in position to substitute them here, and for that I need some space. I do not need it anymore. By the way, I was showing you those vectors because you're going to have many of them later. I'm just warming you up that you're going to see vectors, rotating vectors. We're going to need them actually. At least the idea of them. And before I put them here, I want to take A0 out. I take the A0 out of the summation because now I can now go from the summation from 1 to infinity for both of them because now A0 is out. Right? So I take this and put here. An will come here and here, then I separate them two. So I get An over 2, these two, times e to the I n x plus An over 2 times e to the minus I n x. And I put them into the brackets. Then I have, take this and put here, Bn will come here, here, and then I separate them. I get minus I Bn over 2, this one, times e to the I n x. Then this plus I Bn over 2 times e to the minus I n x. Now what I'm going to do is I'm going to couple these two together. They are same exponentials and I'm going to couple them together. So what I get, A0 plus the summation from 1 to infinity. Look, they are common, so they will be waiting outside. E to the minus, not minus, e to the I n x. And I get here An minus I b n over 2. Then I have these two, and they are common, these exponentials, e to the minus I n x. I get An, and I have plus now, plus I Bn over 2. Now I'm going to name them, I'm going to define them. I call this Cn's, and I call this C negative n. Negative n because I have a negative n here. That's why I chose this name for this. And I call this now, I rename it as C0. That's all. That's what I did. I just renamed them. And you might want to note them because once we have Cn's and C negative n's, later on we might want to find An's and Bn's, the real amplitudes from here. I will move forward. All right, I do not need them. So what I have now is C0 plus the summation from 1 to infinity of Cn's times e to the I n x plus C negative n e to the minus I n x. And that's it. This is the complex form of the Fourier series. This is it. Of course, I can write it in a more compact way that you will see in the books. Look, this sum goes from 1 to infinity. If I choose one number, let's say I choose 5 and I get C5 e to the I 5x, and with that I get C negative 5 e to the minus I 5x, and if I choose 10 then I get C10 C negative 10. So I'm getting negative values too, negative frequency. So why not I do the summation, since I'm getting negative values too, from minus infinity to infinity, and I absorb them. I write Cns times e to the I and x, and that's it. Because whatever the information is here is also there. Because look, now you can count negatives separately and positives separately. Because now it goes from minus infinity to infinity, and you choose minus 5, you get C negative 5. And if you want to choose 100, you get C 100, like this. So whatever is there is also that too. And one more thing, without you and me knowing, this C0 has jumped into the summation already, because somewhere here in between negative infinity and infinity there is 0. When you put n equals 0, you get your C0 back. And this is my Fourier series in the complex form. This is it. Now I have to find you these Cns, these complex amplitudes, and that's my next goal. And before I find you Cns, I want to expand this series. So let me remove it too. Okay, this is going from minus infinity to infinity. So I will start with negative 2. Right? So I write C negative 2 times e to the minus I 2x. Then the next will be minus 1, C negative 1 times e to the minus ix. And then you get C0. Look, your C0 is back. And then you have 1, C1 times e to the I x. The next term will be C2 times e to the I 2x. And then it moves forward. And somewhere here you're going to have ck's. And k could be anything. It could be 10, 15, anything. Ck times e to the ikx, and then it moves forward to positive infinity. This goes back to negative infinity. Alright, now what I do to find Cns, I take my function and I multiply both sides with e to the minus ikx. This is the trick. And I integrate it from minus pi to pi. So I take this and I integrate it from minus pi to pi. The summation from negative infinity to infinity, Cns times e to the I and x, and I multiply with this e to the I minus I kx dx. And now orthogonality is screaming at us. When I take e to the I and x and I multiply it with e to the minus ikx and I integrate it from minus pi to pi, it could either give you 0 if n is not k, and it could give you 2 pi if n is k. And so when you multiply this inside with the integrals, so think of this expansion of the series here. So I take this and I multiply somewhere here, and look, these two are different. N is not k, you get 0. So this integral will go away. And the same applies for, if you take this one and you multiply with that one, again you get 0. So all of the integrals that are not n and k, all of them will die. Only one survives when this e to the minus ikx comes here and multiply with this one, and you put here, because when n is k, this becomes e to the 0, which is 1, and you get integral from minus pi to pi over dx, which is just 2 pi. And so this infinite number of integrals just give you one integral survives. That's going to give you 2 pi, that's here, times cn's, or if you want to write ck's, I will write ck's. If you want to write cn's, it's alright. And so I have found you ck's at complex amplitudes. All I have to do is I have to divide this by 2 pi, and so I get my ck's or cn's. So let me put the result here now. I get ck's, and I divide both sides, this one and that one, by 2 pi, then it gives me 1 over 2 pi, the integral this of the function times e to the minus ikx dx. And that's it. I have found you the series and these complex amplitudes.